You think you know tornadoes. A dark sky, a funnel dropping from the clouds, sirens blaring. That's the version movies sell you. But the real list is far stranger and far more terrifying than anything Hollywood has come up with. These are the most dangerous, bizarre, and downright unsettling types of tornadoes on Earth, ranked from the unexpected to the virtually unsurvivable. Level 1. The Dust Devil. Picture this. Clear blue sky. No clouds. You're walking across a parking lot, totally relaxed, when the ground in front of you just starts spinning. Dust devils don't need storms. They don't need thunderclouds or atmospheric instability in the traditional sense. All they need is hot ground and a light breeze. When the sun bakes the surface enough, air near the ground heats up and rockets skyward. If there's even a slight rotation in the wind, that rising column starts to spin. When it picks up dust, you can see it, and by then it might already be on top of you. Most are harmless, but in the arid American Southwest and the outback of Australia, the conditions can align just right to produce something much more violent. Dust devils have flipped large objects, torn partial roofs off buildings, and killed people in broad daylight with no warning whatsoever. That last part is what makes them so dangerous. No storm sirens, no radar signature, no time. Level 2. The gustnado. The storm just passed. The rain is fading. You look at the sky and breathe a sigh of relief. Worst is over, right? Not quite. Gustnados form at the leading edge of a departing thunderstorm, right where a surge of cold, heavy air slams into the warmer air still lingering near the ground. That violent collision churns up turbulence, and within that chaos, small rotating columns can snap into existence. Fast, violent, and completely disconnected from the main storm cloud above. They don't hang from the sky. They don't have the organized structure of a classic tornado. They erupt from the surface and disappear just as quickly, which makes them maddeningly difficult to identify even for experienced storm spotters. Fences get flattened, roof tiles get ripped off, cars take hits from flying debris, and during large-scale wind events called derechos, massive straight-line storm systems that can sweep across multiple states, dozens of gustnados can form simultaneously along the storm's advancing edge. The storm looked like it was leaving. It wasn't done. Level 3. The fire tornado. A wildfire is already a nightmare. Flames taller than buildings, smoke blocking out the sun, embers flying in every direction. Now imagine that fire starts to spin. When a wildfire reaches extreme intensity, it superheats the air above it so violently that the heat blast shoots upward like a rocket. In most cases, that air disperses. But when terrain, wind shear, and the fire's explosive energy align just right, that rising column begins to rotate. When it contracts and intensifies, you get a visible funnel made not of water vapor, but of flame, smoke, and burning debris. In 2018, during California's Carr Fire, one of these vortices produced winds exceeding 140 miles per hour. That's equivalent to an EF3 tornado. It ripped trees from the ground. It demolished structures. It flung burning material high enough to jump highways, rivers, and fire breaks that were specifically designed to stop the fire's spread. Firefighters have been caught completely off guard by sudden wind reversals caused by these vortices. They're born at the intersection of meteorology and fire behavior, two deeply complex systems that can both escalate in minutes. Predicting them? Still nearly impossible. Level 4. The landspout. Landspouts are the quiet overachievers of this list. They look like slender, almost gentle funnels dropping from clouds that don't even appear threatening. But make no mistake, they're real tornadoes. Unlike the massive supercell tornadoes most people picture, landspouts form from the bottom up. A developing storm stretches and amplifies a small, pre-existing rotation near the ground until a visible funnel appears. Most land at EF0 or EF1, causing moderate damage. shingles stripped from roofs, light objects airborne, trees snapped. But some have reached EF2 strength with winds above 110 miles per hour, enough to tear off roofs and roll vehicles. Their stealth is the problem. They can touch down in seconds beneath clouds that look completely routine. Radar often misses them entirely until it's too late. Level 5. The snow tornado. Tornadoes and blizzards don't belong in the same sentence, except sometimes they do. Snow tornadoes form when extremely cold air moves over a relatively warmer surface, like an open lake or an unfrozen body of water. That temperature contrast creates just enough instability to get air rising and organizing. Add wind shear and the rotation begins. The funnel picks up loose snow and ice crystals, creating a pale, translucent column that's hauntingly difficult to see. In 2013, a winter tornado struck near Shelburne, Ontario, with winds around 90 miles per hour. It collapsed a grain silo and tore apart a barn, in sub-zero temperatures, in a region that had no reason to expect it. Low visibility, falling snow, fading light, and a funnel you can barely see even when it's right in front of you. That's the snow tornado's trap. Level 6. The high-altitude tornado. Most tornado research focuses on flat, low-lying regions where warm, moist air fuels massive storm systems. But the atmosphere doesn't care about altitude. High-altitude tornadoes develop thousands of meters above sea level, where the air is thin and terrain is rugged. The low air density changes the funnel's appearance. It can look narrow, semi-transparent, or flicker in and out of visibility because moisture condenses less easily. But the rotation at the surface is still real, still destructive. Mountain ridges and valleys create localized wind turbulence that can amplify small circulations, and radar coverage in these areas is often blocked by the terrain itself, which means detection is delayed. On July 7, 2004, a confirmed tornado struck Rockwell Pass in California's Sequoia National Park, at an elevation of nearly 12,000 feet, the highest confirmed tornado in United States history. The mountains offer no protection, they just make it harder to see what's coming. Level 7. The satellite tornado. Sometimes, one tornado isn't enough. Satellite tornadoes are secondary funnels that orbit around a larger parent tornado within the same storm. They form when additional rotations inside the supercell intensify on their own instead of merging with the main vortex. From a distance, they can look almost like smaller companions circling the primary funnel in a slow, eerie orbit. They can be just as destructive as the main tornado. And their paths are far less predictable. For anyone on the ground, the reality is this. You're watching the big tornado and thinking you know where to run, and then you realize there's another one flanking it. Level 8. The twin tornado. This one is exactly what it sounds like, and it shouldn't be possible as often as it is. Two fully formed tornadoes touching down simultaneously, side by side, each with its own circulation, its own path, its own destructive potential. In June 2014, near Pilger, Nebraska, twin tornadoes developed within minutes of each other, both reaching violent intensity, cutting parallel paths of destruction through rural communities. Emergency managers were overwhelmed. Radar signatures were nearly impossible to interpret in real time. Escape routes that worked for one tornado pointed directly into the path of the other. Twin tornadoes happen when a storm is powerful enough to sustain two separate rotating regions at the same time, a rare convergence of extreme instability, layered wind shear, and precise internal storm dynamics. When nature can't decide between two tornadoes, it doesn't. It makes both. Level 9. The anticyclonic tornado. In the northern hemisphere, tornadoes rotate counterclockwise. Every meteorology textbook will tell you that. Most of the time it's true. Anticyclonic tornadoes spin the opposite direction, clockwise, and they break almost every rule in the playbook. They typically form along the outer edges of supercell thunderstorms, where competing airflows collide and generate complex opposing rotations. In rare cases, a supercell can split into two separate storms, and the left-moving storm can develop dominant clockwise rotation powerful enough to produce a significant anticyclonic tornado. They look nearly identical to standard tornadoes. The only giveaway is the rotation itself. Because they're so rare, there's far less research data on them, which means forecasters understand their behavior far less clearly than conventional tornadoes. Most have been relatively weak. Some have caused serious structural damage before dissipating. The atmosphere still has rules. This type just ignores them. Level 10. The multi-vortex tornado. What you see isn't always what's there. From a distance, a multi-vortex tornado looks like a single funnel. But inside that outer circulation are multiple subvortices, smaller, intensely spinning columns that whip around the main center like satellites on a very violent track. These subvortices explain one of the most disturbing patterns investigators find after a major tornado. One house completely obliterated. The house next door barely touched. Same storm, same path, completely different outcomes. It's not random luck. It's internal chaos. Vortex paths so unpredictable that the difference between catastrophic damage and minor damage comes down to whether one of those inner columns passed directly over your specific location. Multi-vortex tornadoes are nearly impossible to identify in real time. And the largest, most violent tornadoes on record have almost all contained them. Level 11. The supercell tornado. This is the one. The apex of conventional tornado formation. The system that meteorologists track for hundreds of miles, and that storm chasers pursue their entire careers. A supercell is a highly organized thunderstorm built around a mesocyclone, a continuously rotating updraft that acts as the engine of the entire system. When conditions are optimal, that rotation tightens, descends, and becomes a tornado that can stay on the ground for hours, traveling distances that are almost hard to believe. The most extreme supercell tornadoes hit EF4 and EF5 on the enhanced Fujita scale. Buildings reduced to bare concrete slabs, steel-framed structures twisted beyond recognition, cars and trucks launched through the air like toys. The 1999 Bridge Creek Moore tornado, the 2011 Joplin tornado, the 2013 El Reno tornado. These aren't natural disasters. They're atmospheric weapons. Despite decades of advances in Doppler radar technology and storm research, precisely predicting when a supercell will produce a tornado, or how strong it will be, remains one of meteorology's greatest unsolved challenges. Level 12. The waterspout. When the funnel touches water instead of land, it becomes a waterspout. And there are two completely different animals sharing that name. Fair weather waterspouts form in calm, warm, tropical conditions. They're thin, elegant, almost beautiful. Weak funnels that form from the surface up and typically dissipate quickly. Dangerous to small boats, but usually not catastrophic. Tornadic waterspouts are something else entirely. They form from violent thunderstorms, the same way a land tornado does. The only difference is where they first make contact, and when they cross the shoreline, they become fully functioning tornadoes. No transition, no weakening, no warning. Florida sees more of these than almost anywhere on Earth, thanks to the combination of warm coastal water and near-daily storm activity. At sea, there's nowhere to go, no shelter, no underground room. Just you, the water, and an approaching funnel. Level 13. The volcanic tornado. And then there's this. When a volcano erupts with full force, the violence doesn't stay on the ground. Superheated gases, ash clouds, and volcanic debris blast upward in massive eruption columns. When those columns collide with surrounding air moving at different speeds and directions, extreme turbulence erupts. And within that turbulence, rotating cores can form, intensify, and become visible. The result is a vortex composed entirely of volcanic material, ash at extreme temperatures, rock fragments moving at lethal velocity, near-zero visibility in seconds, lightning crackling through the eruption cloud above it. During the 2018 Kilauea eruption in Hawaii, rotating columns of fire and ash were observed and documented worldwide. These weren't simple swirls. They were structured rotating systems born directly from the eruption itself, and they don't follow the rules. They can change direction without warning. They can spawn satellite vortices. They can split into multiple funnels in seconds. They have no parent supercell, no predictable storm track. They depend entirely on the volcano. And when the volcano enters its most violent phase, these vortices can appear anywhere along that eruption column at any moment. The worst part? We don't fully understand them. Studying them means getting close to an active eruption, and that is not a survivable research strategy. There are gaps in our knowledge that may never be filled. So the question isn't whether a volcanic tornado could form during a major eruption. The question is how far away you'd need to be, and whether that distance would actually be enough.